Wonderful. Then let's get started. So welcome everyone. My name is Sebastian Trimpe. I'm a professor for data science and mechanical engineering here at RWTH Aachen. And it's my great pleasure to welcome you all to today's AI colloquium on behalf of all the directors of the AI Center, to welcome all of you here in the room, as well as in the live stream, and in particular to welcome our guest, Jens Kober. So before I say a few more words about Jens, there's some logistics that I've been asked to briefly mention. This is the agenda. So we have to talk. Now we have Q&A afterwards, and if you have more questions, and also if you don't have any questions, please stay around. We have some drinks afterwards, so please stay here if you want and chat with our guests, with each other, and so on. The talk will be recorded. Live stream will be recorded. The recording, the Q&A will not be recorded, so really ask any question that you may have. We'll also be taking photos, so we assume that you're all okay with this. Otherwise, you know what you would have to do then. The photos for our website, for example. The talk will be available afterwards on YouTube. Again, it will be only the presentation. And if you want to follow us, then please follow us, sign up to our newsletter, and follow us on LinkedIn if you want. All right, that gets me to the most important person of today, of course, which is our guest, Jens Kober. So let me say a few words about Jens. So Jens is a professor at TU Delft. So he's visiting us from the Netherlands. But Jens also has some roots to Germany. And in fact, he received his PhD in Germany in, I think, 2012, right? 2012 from TU Darmstadt and MPI for Intelligent Systems in Tübingen. And then afterwards, he did a postdoc with the Honda Research Institute and also with Bielefeld University. So also some links to Germany there. And then he moved to the Netherlands, where he's currently a professor. And Jens has pretty much won all the important awards that you can win at this career stage in robotics in Europe. And first of all, for his PhD, he received the George Giraud PhD Award, which is the biggest award in robotics in Europe. And then from the IEEE Robotics and Automation Society, he received the Early Career Award. And then in 2022, you also received the Early Career Award by RSS. RSS, Robotics Science and Systems, is the most prestigious robotics conference. And you also received an ERC starting grant. So as I said, pretty much all the big awards that you can win at his career stage. And Jens has broad interest generally in learning and robotics, different many aspects of learning and robotics, and we'll hear some of it today here. And I already mentioned that Jens has many ties to Germany, but I've learned today that you've never been in Aachen. So we are very happy that you visit us today, and we are very much looking forward to your presentation. So I stop taking more time from you, and warm welcome, and very much looking forward to your talk.
Thanks a lot for the very kind introduction. Thanks a lot for the invitation. Thanks a lot for coming. Like Sebastian said, one of my big projects is in ERC starting grant, and the presentation today is going to be roughly about the topic that the grant covers. It's about robots learning through interactions with a human teacher. So already there on the bottom, you can see somebody using a remote control to, in some form, interact with the robot. And I'm going to give you a few more details on that in a bit. But before we do that, I wanted to very briefly think about secrets of human learning. My background is in control engineering, robotics, and machine learning, so this is not going to be scientific. It's just more to set the stage, to think about how humans and also animals learn, and how you can connect it to machine learning or robot learning more particularly. I'm interested in learning motor skills, so that's a form of movements on the order of a couple of seconds to maybe a minute or so. And if people learn that, there are also different ways in which they learn. So there's imitation learning, where the teacher is showing something, and then the student, or the robot in my case, tries to mimic that. That tends to work well for fairly simple tasks, but for more complex tasks, also a robot needs to practice, which we call reinforcement learning. How can people learn efficiently? And in the beginning, if you look at a small child, like I guess he's outdoors now, it takes quite a lot of time until they can do goal direct grasping and reach. But then once people have acquired these kind of fundamental basic skills, they are very good at generalizing them and transferring them to different tasks. So like a complex manipulation skill of taking out a book by first flipping it so you can actually grasp it. So you build up some kind of a library of skills you can combine, you can modify and transfer to new tasks. People also have a notion of intuitive physics. Maybe you don't know the exact equations, but you know that an apple is going to fall. And you can use that to do mental rehearsal to kind of first simulate in your brain what's going to happen and come up with a strategy before you actually try it in the real world. But then there's also interactions with teachers. So here's an example or two examples of what a coach in a sports setting would do. But if you think about interactions of parents with children, you have the same thing. So quite a lot of teaching is happening through interactions. So some form of continued student-teacher interaction where you have intermittent interactions to provide, for instance, additional demonstrations, some other forms of feedback, hints, tips, corrections, and so forth. And you see that more and more in robotic. And I believe that the benefits of that are that it actually helps the robot to learn more quickly, which in turn enables it to learn more complex tasks. And hopefully that's also an intuitive way for people to teach a robot. One last thing, teaching through interactions, that's not only something you do with a child or a fellow human, but we're also quite good at teaching animals in that style. Okay, so that's the very rough idea. Let's go a bit more into the technical things. I'm going to first talk about interactive reinforcement learning, so learning by trial and error. Here's a very old example. It was at the very start of my PhD about learning to play ball in a cup. So the goal is to catch the ball in the cup. It's my cousin's daughter. She was around 10 back then. I took her around 35 times until she could catch it the first time. So how does that look like with the robot? To help it a bit, we showed it an initial good demonstration. So it's imitation learning first, kind of works, but it's still off by maybe a couple of centimeters. And then after 15 trials or so, it's already a lot closer. After 35, 40 trials, it starts to go in. And then after 100 test conversion, you can do it very consistently. So that was already quite good, but if you give it to one of you, it takes more like 20 trials. So I think we can do better. And I'm going to show you how we can do better by using interactions with a human teacher. So before I show you that, interactive learning, what's the setting? This is going to look very similar to a control loop or reinforcement learning loop, if you're familiar with that. So you have an agent, in this case, that's the robot, interacting with an environment, the world. You have some state, could be the position of the robot or some objects they're in, which the robot can sense, and has a policy, which is mapping from the current state to the action it's supposed to take. So a form of controller. It's going to execute an action that changes the state, and then you have to sleep. Now, what we have additionally is a teacher, and the teacher is going to be in the center of it. And for most of the things I'm going to show you, we are going to assume that he or she can observe both the states and the actions the robot takes. And then the teacher is going to provide some kind of feedback or interaction. There's a whole spectrum of different types of interactions we could have. On the one end of the spectrum, you could say the teacher is just going to give you a binary feedback signals, very sparse, 1 if you succeed for the whole task, and a 0 if you fail. That's probably quite easy for the human teacher to do, but doesn't contain a lot of information for the robot that helps it to learn. And then the other end of the spectrum would be to demand of the teacher to provide really the perfect correct action the robot is supposed to do in each and every state. which would make the life of the real robot really easy. Then you're back to imitation learning, but that's very challenging for the human teacher. What we figured out works well for the kind of motor skill-like tasks I'm considering are corrections. So that's going to be correction, not an absolute correction, but just the direction in which you're supposed to change the action. So that's something like move more to the left, move more to the right, move faster, move slower, rather than demanding of the teacher to provide the absolute correct action. So what does that look like? Here I'm going to show you a quick overview of coach corrective advice communicated by humans that my former postdoc Carlos Selemy came up with, which many of the approaches we are using are based on. So the idea is that the car is supposed to drive down on the right side of the road. It already has some initial policy, right, that goes all over the place. And then the human teacher is going to jump in intermittently when the teacher thinks it's going really wrong and provide a correction, move literally more to the left or more to the right in this case. The robot is going to integrate that into its policy, and then hopefully already in the next iteration, it will have learned some things, and the human teacher needs to jump in as frequently. And hopefully, if you iterate that a couple of times, the robot can do it at the speed. So this is essentially an imitation learning approach. Now, the obvious idea for the ball in the cup example would be, let's replace the initial demonstration that Katarina back then gave, with which she actually had to practice quite a bit, with this interactive imitation learning approach. So it would be, first we do the interactive imitation learning with a human teacher in the loop until it's kind of good enough, and then we switch over to reinforcement learning or policy search. That works, but that doesn't offer too many benefits over what I already showed. And then the obvious question is, can we do better actually combine everything in one same learning approach? So what we did there is we have here the exploration. So for reinforcement learning, a robot also needs to try it. So to figure out what works and what doesn't. In a more classical setting, that would be typically some random noise. Once in a while, the robot tries something random. But we can also plug in the human corrections there, actually treat it the same way as the exploration for directions. So we have more classic. And in that way, we can just use a pretty standard reinforcement learning approach. So in a kind of very high level algorithm overview, right now that's the classical setting. How that works is you explore, you roll out the current policies or the current best guess you have, and then you repeat that a couple of times. So that's this loop here, and you add some exploration on top of it when the robot's trying out something new, and then you evaluate each of the rollouts, figure out if it went better or worse, and then you update the policy using all the experience you collected to hopefully improve it. If you want to make it interactive, what we have here is now additionally a switch between the human guidance and the random exploration. So if the human starts to provide corrections and take over, then we're actually going to just use this interactive imitation learning approach I introduced a couple of slides ago to complete the episodes of just one trial of catching the ball in the cup. We store that and then we evaluate how well that one did. Why do we have a switch? If you're trying to correct and at the same time the robot tries some random stuff, that tends to get very confusing. So that's why we decided to switch off the random exploration once the human teacher starts to interact. So it looks something like this. Now we can actually start from zero. The robot is just standing still, not doing anything. What you can see is Carlos sitting in front of the robot and by actually providing corrections of move more to the left, move more to the right, like I was saying before. And then after 20 trials or so, it can catch the ball at the cup. So that's not really almost as fast as a human can do the task, him or herself. What does that look like if we also compare it to more classical approaches? What we have on this axis is the number of rollouts, number of times the robot tried. And here we have costs. So in this case, lower is better. In red, the red curve is using a standard reinforcement learning approach. The green one is using interactive imitation learning, and then the blue one is this combined one. What I need to tell you additionally is that the plots I'm showing you here are including an English demonstration. So like the first version of the ball in a cup example I showed you, we had somebody demonstrate it first, and they can just try to play it back. And it only needs to fine tune. So yes, reinforcement learning takes a bit longer. It's not drastically longer, but you can see is that you only use interactive imitation learning. Initially, it's a bit better, but then it levels off just because you start to hit kind of the accuracy limits of the human teacher. While if you combine it with reinforcement learning, initially it takes a bit longer, but then you also can get a final performance. Now the picture changes quite a bit if we learn from scratch. So if you initialize the robot with 0 effectively. The interactive imitation learning and interactive reinforcement learning take a tiny bit longer, but you see it's essentially the same thing. But now, if you try to learn such a task with reinforcement learning, it takes around 200 tries, so order of magnitude longer. One important thing to note here is this obviously only works if the goals or the reward function of the robot and the human are aligned. If the human is trying to teach something completely different than what the robot is optimizing for, well, it's not going to harm it. It's just going to ignore it because we are effectively scoring everything the human does before we do the update with the reinforcement learning. We're just going to lose all the demonstrations that the human teacher provides. So that's one idea of how you can combine reinforcement learning and robot is trying to optimize cost function or reward function with corrections of the human teacher. And really the idea is people are very good at providing the high-level general rough trajectory, but not so good, like we can also see in this plot here, at fine-tuning it, while the robot learning approaches are typically very good at fine-tuning stuff and doing it very consistently. I'm going to switch gears a little bit and talk about interactive imitation learning. And I'm also going to switch to a slightly different setting where we're not so much interested in the details of the movement, but more in the sequence of movements. For imitation learning, we don't usually just want to reproduce and replay exactly what we demonstrated. That would be kind of boring. Rather, we want to also have the robot generalize to a related but new situation. So for instance, one of the typical things is you want to pick up a glass like this one, but you also demonstrate it like that. But then you also want to be able to pick it up if it's on the other side of the table. So then what the robot needs to figure out is whether it's supposed to move relative to the glass, relative to the table or the board or whatever. And if you make it even more complex and we add a coaster, then as long as the cup is on the coaster, it doesn't really matter if it moves relative to the coaster or relative to the cup. It's going to be exactly the same trajectory. And if you move the two of them together, it's still going to. So that only becomes interesting once you separate the two objects. And here we really wanted to make that interactive and use the human to disambiguate which reference frame, which object is the relevant one, but then not to bother the human if it doesn't make any difference for the current situation. So concretely, that means as long as the cup and the coaster stay together, it's going to determine, okay, the movement is going to be the same, so I don't need to ask the human, and only if you separate the two objects, it will ask. So here's an implementation of that. We already taught it how to move the cucumber to this box. It can generalize the different position of the cucumber, but now what happens between the clip I was showing you a second ago and here is that we swap two crates. And now the question is, should it still move relative to the default coordinates, so down here, or should it move relative to the correct? Now it's going to start doing it. It figures out, oh, it's ambiguous. I don't know what to do. And then Giovanni, my PhD student, just gave it a little push in the right direction. And now I figured out, okay, that's the correct one in this situation. I've resolved this ambiguity. And from then, it can do it. We also did a user study with that, a different task of stacking some coordinates of t in this case in the correct order. There we compared kinesthetic demonstrations. So there you move the robot around and provide a whole lot of demonstrations on the correct order. And there you actually need to keep in mind all the possible combinations the robot would encounter, and then provide sufficient demonstrations so there's kind of, you can statistically figure out which the correct object is. That can be quite tedious, and people tend to forget one of the combinations, and then you need to go back and add more. So effectively, it's some form of interactive anyhow. And then we compared it to either learning interactively to resolve ambiguities, where you just provide one initial demonstration on how to do the rough movements, and then it does it largely autonomously. And if it doesn't know what to do in one situation, in this case it was a screen interface, you press a button on what to do. Results look something like that. Who's familiar with the TLX? Yeah, not too many. So it's effectively a questionnaire, and you have the different categories like mental demand, physical demand, temporal demand. You ask how well the robot performs, how high your effort and frustrations were. So low is always better. And here KT is kinesthetic demonstrations compared to either. And as you can see, the interactive approach was scored by all participants consistently as better. And also if we ask them verbally, they largely prefer to do it in this way. So coming back to movements or motor skills, what I showed you so far was a bit more classical based on known states, some low-dimensional states, but then nowadays this can be also do deep learning with that and deal with high-dimensional inputs like cameras. You could, in principle, apply it, but it's just going to take an awful lot of time if you want to bring everything together. So what you could also do is you collect a bunch of data from the scenario you're interested in, not necessarily exactly the task you want to do, and then you use some form of encoder-decoder structure to learn some form of a compact latent representation, so some form of a state representation, and on top of that we can then learn the policy. So the idea here is that you train this kind of funnel-shaped structure to compress the image to a small representation, and then you decompress it again and you try to minimize the difference between those two. And then as next step, once you have a good representation, you disable this decoder part, this kind of reconstruction part, and we learn a policy of that. So then hopefully you can go back to roughly what we had before. But this setup works if you do it sequentially. You obviously need to have some data first, then you need to make sure that the data is representative, and then you need to still do the corrections. Again, the question is, can we do better and do everything in one go? Something like that. Initially, the corrections are potentially not going to be very helpful because it's trying to learn at the same time what a good representation is. But effectively, in the beginning, people are more or less operating the robot now, so it doesn't make that much of a difference. So then really, you try to learn both things at the same time, policy and the reconstruction. In this case, the reconstruction is an auxiliary loss. We're really mainly interested in the policy and being able to reproduce what a human is demonstrating, and the reconstruction helps us to find a good representation. Looks something like that. On the left, you see the latent representation of the reconstruction there. Also, initially, I was just blind, and then pretty quickly it learns some form of reconstruction where you can roughly make out the details. Again, you can't really see the corrections we provide, and the task is just to push off the whiteboard marker from the table. And because we're not really interested in the quality of the reconstruction, it's a bit grainy, and maybe if you could do a lot better, but that's good enough for the control. And then after 20 minutes or so, it can do it completely autonomously with various different positions of the whiteboard. And then similar to that, just to show an example that was very similar to my running example, ducky town environment, drive on the right side of the road. On the top, you see what's happening. You see the raw camera image below the reconstruction. Rodrigo, my PhD student, is using a keyboard to once in a while provide corrections, and then you can also do some instantaneous validation. Just take your hand off, see how well the robot does. If you're happy with its performance, you're done. If not, you can just continue providing corrections. And also there it takes about 20 minutes or so. That was a somewhat slow task, just taking a single image. But for more complex tasks, if they're dynamic or you need to keep some other kind of memory, that won't work. So then the obvious thing to do is either try to stack some input images or add a recurrent structure in neural networks. In this case, currently an LSTM unit. And additionally, what changed is now the decoder is not going to reconstruct the direct observation we get, but actually the observation in the next step. So that forces the transition model to also learn about the dynamics, and we can do it because we collected data and then only do updates in a little batch. And then the rest stays the same. We also train the policy in parallel. And then it looks something like that. It's a little pendulum or disk on that weight on a disk, which is equivalent. On the left, the camera input, on the right, the prediction. And then something like that after after 12 minutes. So you can really see if we block the view, it doesn't know what to do. It's really only using the images and the predictions to do the swing. And what's also maybe interesting about this little task, seems simple, but it's way too fast to actually teleport and control it. But you can quite easily teach it with these interactions because the robot is supporting effectively with its own policy. Other example of that, the robot is supposed to pick some oranges and touch them. The only thing it can see is, use my mouse instead, is this white part here. So it needs to memorize where the oranges are. And after 15 minutes, it can do already quite well. And then after 45 minutes, it has converged. And what we're doing here is now we are randomly covering some of the oranges with pairs, and it's supposed to avoid those. Because it already has a good representation or state representation and some initial policy, it's really quick to adapt this policy to the new task. Like already after 3 minutes, it can do the new task, and then after 10 minutes or so, it has nicely converged. The examples I showed you so far, we were mainly providing feedback in direct interaction space. That has some advantages, it's very direct, but if you think about a slightly more complex robotic system, then it very quickly becomes high dimensional. And if you want to have non-robotics experts thinking about the inverse kinematics of a robot, that starts to get very non-intuitive. So why not do it in state space instead? Well, then you need some form of inverse model for just a robot. That's what the manufacturer provides you, so yes, you can use it there. But you can also learn it at the same time as the policy. So in this task here, the task is to write with a laser pointer on a whiteboard. So we know potentially know the inverse kinematics of the robot, but we don't know the transformation between the robot and the whiteboard. And the corrections we want to provide are supposed to be in the space of the whiteboard. So there we indeed learning at the same time the policy and the inverse dynamics and inverse kinematics to write some letters, and also here it takes 10 minutes or so to teach the task. Yeah, so those were mainly kinematic movements, kinematic trajectories, but things become even more interesting if you go beyond, if you're interested in really quick movements, or if you have contacts and forces. So for contacts, you would want to either learn a force controller. In this case, we decided to go through an impedance controller and learn not only the trajectory, but also the stiffness profile. What we did there is we first provide a kinesthetic demonstration, so that's the part in blue, and then we learn a Gaussian process-based attractor. And then to initialize the stiffness, it's just the same for the whole state space. Because this robot doesn't have a force torque sensor, you can't really jump in and correct it by touching it, but it's executing the task. So we decided to use some form of teleoperation in space mouse in this case. And then it is learning from these corrections both how to modify the trajectory, so that's the little dashes here, but then also how the stiffness should be modulated throughout the trajectory. And then overall, we have a stabilizing field that pulls the robot back to the normal trajectory. So it looks something like that. First demonstration. And if you play that back, it doesn't know that it's supposed to apply a force. It doesn't know that the attractor is supposed to be below the surface of the table. So now I'm asking to push down on the space mouse to provide a correction. It's supposed to go down, and also to increase the stiffness in the part of that movement. So you can see it here, there it's going to shoot up with the stiffness for the part where it is in contact. So with only one correction, one round of corrections, we can actually teach the task here. And we also tried that for unplugging and similar tasks. So it looks something like that. What you see in the plot is a view from the side. So the table is here effectively. In black is the final trajectory. In red, you see what we demonstrated initially, and then the background colors show the forces it applies, the resulting forces, and then the little blue arrows show you the direction of the movement. So you can see that no matter where you start, it's always going to pull it back to the nominal trajectory. We can also try something like that, where the task was to restock in a supermarket environment. Also there, an initial demonstration, and then some interactive corrections. Now, we wanted to actually also speed up the movement quite drastically to get it to below 5 seconds. So there, the kind of interface we came up with allows you to separately correct the trajectory and separately increase the speed. One other interesting tidbit is that the timing of the gripper is very, very imprecise, so it was plus minus half a second. So we really had to teach a trajectory that is robust to that inaccurate timing to do the task. And then here, that's the final movement in real time. And then we also did a little user study with that, with a simplified task of just putting an object to a different place. What you can see here is that if we have some form of sensing, we can also generalize to moving objects. And what you just saw with pulling it far away shows the stability that if it's so far away that it's totally uncertain about what to do, it's just going to stop. So what we try to do there is compare asking people to correct everything at the same time, so both correct the trajectory and speeding it up, versus splitting that into correcting first, either correcting the trajectory or speeding it up. And we thought it's going to be a lot easier for people if they can concentrate on one thing and allow them to decide, okay, I now want to focus on correcting the speed, or I want to correct the trajectory. Turns out we were only half right. It was a really nice bimodal distribution. Some people really prefer teaching everything at the same time. So that's just a lot more intuitive. I can do everything, and I don't need to decide beforehand. And the other half of the people really strongly prefer to teach it separately, like we had intended. So what does that mean? Unfortunately, there's a quite big variety in people, so there's probably no one-size-fits-all solution for this kind of interactive teaching interfaces. Then the more or less the last thing I wanted to show you is a more complex task that's from a hackathon last year for ERF that our team won. So it's somewhat inspired by disassembling waste or diffusing a bomb or something like that. Again, we started a kinesthetic demonstration, and it's actually subdivided into several parts of the movement. But then also here, if you just use the demonstration, it doesn't apply enough force, and you need to fine-tune some things with interactive corrections. And then it can actually correct generalized to various positions of this box. What you see here is we also implemented some additional little robustness things like searching for the keyhole, and all those things very reliably. Again, we're using impedance control, and with the corrections, you can actually make the movements themselves also robust to small variations. So to sum up, I hope I managed to introduce teaching through interactions and could convince you that this is a promising way of teaching robots in this case. If you think about robot learning, it has the potential to drastically speed up the learning process by picking the human's brains. Because, like I was saying before, it has complementary strengths and weaknesses to how humans can teach and what robots can do on their own. And also you can combine that with many other ideas in robot learning, like pre-training with data for the perception, combining it with training and simulation, transferring it, coming up with some kind of curriculum, doing meta learning, and then only using that for fine-tuning and so forth. They actually wrote a massive, almost 200-page survey on that last year, if you're interested in more details on that. But the big open question still is, and I was touching on that with the second to last example I showed you on how do humans like to teach. So, to wrap up, I guess most of you know this little quote by George Box: all models are wrong, but some are useful. If we apply it to my setting, maybe we can change it to all humans are wrong, but most are useful, provided the corrections. So really, what I was talking about seemed to be maybe a bit like we want to have humans help robots to learn quickly. That's true, but actually the ultimate goal is not to have people help robots to get unstuck, but really help them to learn new tasks quickly so that they can support us in our daily lives. I'd like to say a huge thank you to all the people that did the hard work and often the things I was presenting today, and the people and organizations that provided funding. And thanks a lot to you guys for joining, listening, and I hope you have many questions. Thank you.
Thank you very much, Jens, for this wonderful and very inspiring talk. We have time for Q&A questions. I can